Hello everyone and welcome to a fresh lesson in engineering geology. Today we are going to discuss about the chemical characteristics of minerals. If you recall, the last time around we talked about geometric and physical and optical characteristics of minerals. Today we are going to have a look at the chemical features that give rise to those physical properties. Before we begin with the subject matter of this particular lesson, we are going to consider the question set of the previous lesson. I am going to give you the answers. The first question that I asked was on birefringence. What is meant by birefringence? Now, birefringence is an optical characteristic by which there is a double refraction of a waveform of electromagnetic waves that tries to cross a chemical a mineral crystal. Now, the second part of the first question was whether you would expect a halide crystal to be birefringent. Now, I said in the last lesson that if you have got a crystal that is isotropic, then it is not going to exhibit birefringence, and as a result halite is also not going to be a birefringent crystal because halite is an isotropic mineral. Now, the second question that was asked was you were given an XRD pattern for a sample and you were asked to identify one of the constituent minerals of the sample for which the XRD pattern was provided. Now, what I have done, I have put the XRD pattern that was given to you in the last question set on the left here, and that is shown. I am going to just draw a line on top of the XRD pattern provided to you because the line thickness was not adequate, so that the resolution may not actually pick the input XRD pattern. Now, this is the XRD pattern that was given to you. So, as usual, intensity is on the vertical scale, and on the horizontal scale you have got the angle 2 theta that was explained in the last lesson. Now, what I have done here, I have put side by side the XRD signatures of 3 clay forming minerals on the plot shown on the right side, on the right bottom of the slide here. So, let me actually highlight here the pattern that you would expect for a montmorillonite crystal, and not for the montmorillonite, actually kaolinite crystal, sorry. So, this is the signature of a typical kaolinite crystal. Okay. So, now what you can see is that for the constituent mineral, for the mineral unknown mineral that is provided to you, you can see there is a peak at about 12 degree value of 2 theta, and in kaolinite also we have got a peak at a similar angle, and also you can see that another intense XRD signal was obtained at about 25 degree value of 2 theta. Now, for kaolinite also we have got a distinct signal at 25 degree value of 2 theta. So, from this we can approximately say that one of the constituent minerals of this particular sample is kaolinite. Okay, so that takes care of the last question set. Now we get back to the subject matter of this particular lesson. Now, what are the objectives of this lesson? We are going to actually list a set. We are going to list major chemical constituents of the Earth's surface. We are going to identify the chemical structure of silicate minerals, carbonate minerals, oxides and sulfides. These are the major major building blocks of the crust of the Earth, as we will see in the course of this lesson. And finally, we are going to identify the sources and chemical characteristics of common minerals. In other words, how these types of individual minerals form. We are going to briefly discuss those items. All right. Now, what is the composition? What is the chemical composition of the surface of the Earth? As we have seen, the surface of the Earth is called the crust of the geoid sphere. And what is the constituent of that? A large part of the Earth's crust is composed of oxygen, and the second most abundant building block of the Earth's surface is silicon, as is shown on the pie chart of this particular slide. And there are several other constituents. The next most abundant one is aluminum, and then you have got iron, calcium, sodium, potassium, magnesium, titanium, hydrogen, and finally you have got the remaining chemical constituents that are clubbed together as others. So, the most abundant minerals are composed of then silicon and aluminum. So, it is logical then to consider how the structure, how we are going to, what kind of chemical structure we are going to get for silicate minerals. Now, in order to do that, what we are going to do, we are going to look at the building block of the silicate minerals. And the basic building block of silicate minerals is a silica tetrahedron. Schematically, it is shown on the right. You can see that you have got a silicon atom. You have got a silicon atom near the center of the tetrahedron, and at the four corners of the tetrahedron there are oxygen oxygen negative ions in the corners of the tetrahedron, in the corners of the tetrahedron. So, silica atom is at the center, and there are four oxygen ions at the corners of the tetrahedron. Now, this is a schematic. You should realize that the cartoon that is shown on the right of the slide is actually a schematic, and in order to prepare this, we did not consider the relative size of the atoms of silicon and oxygen. Now, if we do that, then the picture that we are going to get is kind of shown on the left side of the slide here. So, this one is a depiction considering the geometry, considering the size of the individual atoms that is with which the silica tetrahedra is composed. Now, what we got here, you can see that the silicon ion is at the center, or actually silicon atom is at the center. This is the silicon, and then much larger oxygen ions are shown like this. This is the same thing, I mean the structure of this one is same as the tetrahedron, but I just changed the relative size of the ions here on the right, because it is difficult to comprehend what is the exact look of the tetrahedra from the figure that is shown on the left, but the figure on the left gives you an idea about the relative size of the silicon ion of silicon atom and oxygen atoms. Okay. So, then you can to reiterate what we wanted to say is that silicate minerals will be composed of different combinations of unit structures, and these unit structures are essentially tetrahedral in shape, and they are composed of a silica ion at the center and 4 oxygen ions at the corner of the tetrahedron. Now, let us look at how these individual building blocks combine to form different types of silicate minerals. Now, the first group first subgroup of the silicate group of minerals that we are going to consider here will be single chain and double chain. Single chain structure is shown on the left of the slide here, and here what we got is you have got silica tetrahedra oriented in an opposite manner like this. So, what happens here is that for each silica tetrahedron you have got 2 oxygen minus ions are shared with other tetrahedra. So, what you got here is essentially a 1:3 combination of silicon and oxygen, and then you have got each of these chains, they are going to actually combine with each other with different types of cations. Now, what happens here then, you have got silica and 3 oxygens, and the chemical structure, I mean the chemical formulation of a single chain silicate mineral will be having a radical which has got this type of Si, which has got a composition of SiO3. Now, let us consider what is meant by a double chain. Double chain minerals are shown schematically on the right of this particular slide, and what you can see here is that 3 of the oxygens here, actually rather 2 oxygens of each tetrahedron is shared again with other tetrahedra in the same chain, but what we got here, which is unlike the previous one, is that another oxygen for the for another oxygens here, they are also shared with an opposite with a sort of like a mirror image of a chain which forms on the other side. So, this chain here is combined with another chain by sharing of oxygen atoms like these. So, it is obvious that in this case you have got more number of oxygen atoms, oxygen ions are shared amongst different silica tetrahedra, and as a result the silicon to oxygen ratio is different in case of a double chain, and here the ratio between silicon and oxygen is, instead of 1:3 in case of single chain, here what we got here is a 4:11 distribution of silicon and oxygen. So, what you got here is that you are going to get radicals that are going to be Si4O11. This type of radicals will keep on appearing in the chemical composition of double chain silicate minerals. We are going to look at the examples, individual examples of these types of minerals in due course of this particular lesson. Now, let us move on to the next types, other types of silicate minerals. You imagine that what we did, we began with an individual silicate tetrahedron, then we could combine these tetrahedra in a combination of a single chain as we began, then we got a double chain structure, and if we extend this particular concept a little bit further, then we are going to get a structure which is known as sheet silicate. So, what you got in sheet silicate is that you have got a two-dimensional network, essentially of silicon tetrahedra. So, here for instance all these individual triangles indicate silica tetrahedra, and this particular framework, this particular structure extends horizontally both ways in the plane of the tablet here as well as vertically in those direction almost indefinitely. So, this particular type of structure is called sheet silicate, as the individual tetrahedra, they combine with each other and they form individual sheets. So, here you can see more number of oxygen ions are shared between different tetrahedra. As a result, the oxygen as a percentage of silica will be even smaller in comparison with a double chain silicate mineral. Now, a particular type of silicate mineral, you will get a structure which is not an indefinite extension of a two-dimensional mesh in a plane, but it is a ring like structure as shown on the right here, and for obvious reason this type of mineral is called ring silicates. Here you have got basically a series of silica tetrahedra that combine with each other to form a ring like structure. These minerals are relatively less abundant in comparison with other type of silicate minerals that we have so far discussed. Now, if we extend the concept of sheet like structure a step further and we consider a three-dimensional structure instead of a two-dimensional one, then we are going to end up with a type of silicate which is known as framework silicate. So, in this case what you get is tetrahedra combined with each other in a three-dimensional sense, and you have got a solid formed out of combination of silica tetrahedra in three-dimensional in all the three directions instead of the two directions that we considered in case of sheet silicates. Now, in addition to all these things, we can also have a self-contained silica tetrahedra. So, in addition to all the types we considered here, we can have a single tetrahedra. Many types of minerals, as we will see later on, will be comprised of single tetrahedra instead of a combination of several tetrahedra as we have considered here, or there are minerals which are composed of double tetrahedra, and double tetrahedral minerals are more rare than all the other types of minerals, silicate minerals, that we have discussed in this case. Okay. So, that actually gives you the chemical structure essentially of different types of silicate minerals. Now, let us consider individual rock forming minerals which classify as different types of silicate structures that we just now discussed. So, the first one that we are going to consider, the simplest one, is the isolated tetrahedra. So, in this case, what you got is you would not have any oxygen sharing, and the structure and the chemical formula that you are going to get for this type of minerals is going to be either X2SiO4 as in case of an olivine mineral, or X3Y2SiO4 3 as in case of garnet group of minerals. By the way, I want to actually mention here that isolated tetrahedra are perhaps the most stable and most they are the hardest and the most stable minerals of the silicate. They form the most stable and the hardest group of minerals of the silicate family of minerals. Now, you can see that the olivine has got a hardness of 6.5 to 7, and garnet also has got a hardness of 6.5 to 7. Now, let us move on to the single chain. In single chain, we noticed earlier that you have got one oxygen shared, and these formulae, the chemical formulae of this class of minerals typically will look like this: XY Si2O6, and by the way, you may have already understood that by X and Y I am indicating cations of different types, like calcium or magnesium or potassium or iron or aluminum, or there could be other types of cations as well. These are just a few examples of abundant cations. So, here what you will get is a chemical formulation comprised of a formula like XY Si2O6, and this one, this type of formulation is typical of the pyroxene group of minerals, and these minerals have got a hardness of 5 to 6, and notice that these minerals cleave at 93-degree angle. They cleave more or less at orthogonal in orthogonal planes. So, if you want to actually shatter a pyroxene group of mineral, or rather if you want to actually break a mineral composed of single chain silicates, then you are going to cleave the mineral at in planes that are almost orthogonal to each other. This is important, as we will see when we consider a double chain mineral. We have already seen that a double chain mineral in case of a double chain mineral, you have got two to three oxygen atoms shared between different tetrahedra, and an example of this class of mineral is amphibole. One of the minerals of the amphibole group is hornblende, and hornblende has got a hardness of 6, and notice the cleavage angle. In this case, this particular type of mineral actually cleaves at 56° angle. So, this is the angle of cleavage. Now, you should actually notice that double chain minerals cleavage of double chain minerals is very similar to 120° or 60°, and this is in contrast with a single chain which we discussed just in the previous slide, which cleavage of single chain is approximately equal to 90°. So, single chain minerals, if you break them apart, then you are going to get orthogonal cleavage planes, almost an orthogonal cleavage planes, but in case of double chain you will have cleavage planes that are oriented with respect to each other at 120° or 60° angles. Chemical formula in this case, it will contain a radical which is going to have this type of structure, Si8O22, and this is a 10 negative electrical charge. Then we move on to ring silicates, and in case of ring silicates, what we have already seen that again many of the oxygen, actually there is a mistake here. 2 of the oxygen atoms are shared in case of ring silicates, and one of the examples of a ring silicate is tourmaline, and tourmaline has got a hardness of 7, if you recall. Now, I would also like to bring to your notice that these type of crystals also has got a trigonal symmetry. We noticed in our previous lesson that if you have got if you consider a tourmaline crystal, then the tourmaline crystal can actually it has got a threefold symmetry when you consider a tourmaline crystal. Let me just bring to your memory the shape of the tourmaline crystal. Actually, it is going to be like this, and here on the other side it is going to be like this. So, this type of crystal has got one symmetry axis here, another axis here, and another axis of symmetry. The drawing is becoming awful. Another axis of symmetry is going to be on that angle. So, these axes of symmetry are again oriented at angles of 120° with respect to each other. And if you remember, this one, the crystal here is going to be a prismatic form, and in 3 dimensions it is going to have a look approximately as shown on the sketch that I have just drawn. Okay. So, that kind of takes care of ring silicates as well. Reverting back to the slides. Now, the next group of silicate minerals is the sheet silicate, and in case of sheet silicate, what you got is all oxygen atoms in this case are going to be, all oxygen ions in this case are going to be shared. Now, you remember I indicated in the last slide, there was a mistake in the last slide in which I was saying that in case of ring silicate you have got all oxygen ions shared, but that was not correct, and in case of ring silicates you have got just like sheets, just like a two-dimensional, I mean a double chain, you have got two oxygen ions shared, but here what you have got all oxygen ions shared in case of sheet silicates. And a very obvious example of sheet silicate is the mica, and mica has got a hardness of 2.5 to 3, and then in the finally we move to the framework silicate and aluminosilicates, and in this case again you have got all oxygen ions shared. That means covalent bonds form out of all oxygen ions, and an example of that is quartz. It has got a hardness of 7. Plagioclase feldspar, it has got a hardness of 6 to 6.5, and the formulas of plagioclase feldspar are also mentioned on the slide there. These are basically calcium aluminosilicate or sodium aluminosilicate or potassium aluminosilicate. Okay. So, that kind of brings us to the end of different subclasses of silicate minerals. Now, we need to look at how different silicate minerals form, what is the origin, how the silicate minerals form in the nature. So, one of the sources of silicate minerals is from cooling of magma or metamorphism. So, this is the primary source. So, most of the silicate minerals are formed by cooling of magma or from metamorphism. Now, weathering, deposition and diagenesis, that also is a source, could be sources of silicate minerals, and as we will see later on, sandstones, siltstones, clay stones and shale, they form in this manner, and by weathering, deposition and diagenesis actually chemical composition of minerals could also change in the process. And the third source of silicate minerals is chemical precipitation. Now, precipitation of amorphous silica from seawater is the mechanism that is responsible for this for formation of flint and chert type of minerals. Okay, so basically then you could get silicate rocks formed out of cooling of magma or metamorphism, or from weathering and consequent alteration of the chemical characteristics of the original silicate mineral, and also you could get silicate rocks formed out of chemical precipitation, as in case of flint and chert. Okay, that ends the discussion on silicate minerals. The second most important mineral group perhaps is the carbonate mineral group. The key building block in this case is the CO3 2- radical, and this is basically a planar triangle, and in this case what you got is the carbon atom is at the center. In this case you have got the carbon atom at the center. Okay. So, what you got in this case is carbon atom at the center, and then you have got oxygen ions, carbon ion at the center and oxygen ion at the three corners of the triangle. So, basically this is the carbonate type of structure. So, so if you recall, then each one of these things have got two negative negative charge, and carbon will have 4 positive charges. So, the balance of this is negative of -2. So, a carbonate ion has got a charge of negative -2. So, this is a planar structure as is indicated on the slide. Now, what are the typical properties of the carbonate group of minerals? One of the very important property is varying degree of solubility. It actually solubilizes in water to a varying degree. Now, it also reacts with mild hydrochloric acid. So, these are the two key properties of carbonate group of minerals. What are the examples of carbonate group of minerals? The most abundant mineral perhaps of the carbonate group is calcite, and the other example of the carbonate group is the dolomite, and also you can think about several others like limestone. Now, I would also like to mention here that calcite has got a chemical structure which has got a formula of XCO3. For example, you could get calcium carbonate. This is perhaps the most abundant one of that group, or you could even get calcium magnesium carbonate, which is actually which is called the dolomite, Now, aragonite is another mineral that also has got a chemical formula of calcium carbonate. I mean, it is the same thing as CaCO3, same as calcite. This also has got the same chemical formula as calcite, but the structure or the geometry of crystals of calcite and aragonite are totally different, as we will see later on. So, this type of different minerals which has got the same chemical formulation, but different physical appearance or different crystallographic characteristics, this is called this type of minerals is called polymorph. So, aragonite is essentially a polymorph of calcite. Aragonite is a mineral that is more rare actually than calcite, and that aragonite forms under high pressure but low temperature environments. Okay. What are the origins of carbonate minerals? Carbonate minerals have got a biogenic origin, or it could be deposited from the calcite particles from pre-existing rocks by the action of water. So, water can solubilize calcium carbonate from pre-existing rocks, and it can deposit that through an inorganic process, and that also could give rise to calcite rocks. Dolomites actually forms from a process that is known as dolomitization, and this is basically by replacement of calcium ion with magnesium ion of the pre-existing rock, or from direct deposition of water that is rich in magnesium ion. So, basically carbonate minerals, they originate from precipitation process. It could be either organic process, it could be either an organic precipitation process, or it could be an inorganic process from seawater, or from the action of water basically. Okay. Now, as I indicated earlier, I gave you the example of two polymorph crystals, two polymorph minerals, calcite and aragonite, and these two types of minerals is shown schematically here on this slide. You can see that the one on the left is of mineral calcite, and this has got a trigonal symmetry. This has got a trigonal symmetry or a threefold symmetry really, whereas when you consider mineral aragonite, then you have got a twofold symmetry only, and this is essentially a rhombohedral structure which was discussed briefly in our previous lesson. Now, the basically in this case what you have got, the hardness of calcite is 3, whereas hardness of aragonite is 3.5 to 4, and I indicated the crystallographic symmetry as and it is also mentioned here. Now, I also indicated that aragonite mineral is more rare than calcite. Calcite is more abundant, and now the question comes that, and actually I also would like to mention that this this type of mineral, actually aragonite, is in a sense an unstable mineral under the normal conditions of temperature and pressure. Then the question comes, how do you get this aragonite mineral at all? Now, aragonite minerals actually forms from calcite, could form, that is one of the ways aragonite minerals could form is from the metamorphism of calcite rich rock. So, if we expose calcite rich rock in a high pressure environment, you could end up with a rock that is rich in aragonite mineral. Now, that actually gives you an example also of how how different types of minerals change in chemical characteristics when you expose them to different types of pressure temperature environment, and we will examine this one in more detail when we consider metamorphism later on in this course. Now, the third example is given here is of dolomite, and dolomite has got a hardness of 3.5 to 4, and this has got a trigonal rhombohedral symmetry, just quite actually trigonal rhombohedral symmetry, and the symmetry in this case is quite comparable to the symmetry of calcite as indicated on the left on the leftmost cartoon on this slide. All right. Okay. Now, another mineral group that is also quite abundant are formed of different types of oxides. Now, as the name suggests, in this case you will get oxygen ions, O- anion present in the chemical structure. Examples of this class of minerals are oxides of iron, hematite, and magnetite. Now, hematite has got a chemical composition. Hematite has got a chemical composition that is composed of trivalent iron, whereas magnetite has got a chemical composition that has got bivalent as well as trivalent iron in the chemical structure. So, they are very similar. They are very similar to each other in a sense. Let's let's look at this thing because that could be of interest. Now, hematite has got a dark red to blue black in color, very dark color in fact. It has got a deep red streak. The specific gravity of hematite is 5 to 6.5, hardness is 6.5, and if you compare these properties with magnetite, what you get, again you have got grey black color, which is again a dark color. It has got a black streak, a deep colored streak again in comparison with the hematite, and then it has got a hardness of 5.5 to 6. Then again the hardness is again not very different from the hardness of hematite, slightly lower perhaps, and it has got a specific gravity of 5.2, that also well within the range of the specific gravity of hematite mineral. Now, the basic difference that you get in these two cases is that hematite exhibits magnetism after being heated. Hematite in fact is weakly magnetic, whereas magnetite is strongly magnetic, and hence the name of that particular mineral. So, the most obvious way of classifying hematite mineral from magnetite mineral is by looking at the magnetic property of these two types of minerals. Okay. Another relatively abundant group of minerals are called sulfide minerals, and here you have got bivalent sulfide, bivalent sulfur anion or sulfide anion, and these things, examples of these things are pyrites and galena. So, if you recall, we looked at the crystal structure of pyrite and galena in the previous lesson, and pyrite in a sense is ferrous sulfate, and here what we got is a bivalent iron, ferrous sulfate, and galena is essentially lead sulfate. Pyrite, if you recall, it has got a golden color. This thing is also called fool's gold because of this. It is not a precious metal, but it has got an appearance which is similar to gold. It has got greenish black streak, specific gravity of 5, and hardness of 6.5. By the way, the hardness that I am talking about in this lesson is in the Mohs scale, which we discussed in the previous lesson. Galena, on the other hand, it has got a dark grey color, dark grey streak, it has got a hardness of 2.5 and specific gravity of 7.5. Now, we look at the origins of oxides and sulfide mineral, oxides and sulfides. Now, oxides form out of igneous or metamorphic rocks, from volcanism, that which is, this is the source of many oxide minerals. And iron oxide, by the way, iron oxide forms out of chemical precipitation. Some of the ferrous minerals also form because of biogenic action, quite in similar manner as of a biogenic carbonate mineral. Then sulfides actually form out of igneous, out of volcanism or metamorphism, or it could be formed out of mobilization of sulfide minerals and redeposition through the action of, through chemical action, chemical weathering. Okay. Now, this cartoon here, this slide here shows a few examples of unit crystals of sulfide minerals, oxide and sulfide minerals. Now, hematite we discussed, it's an oxide mineral, and it has got a it has got a unit crystal that is shown on the left. Magnetite, it is again an oxide mineral composed of bivalent and trivalent iron, and the crystal is shown on in the middle here, and a sulfide mineral galena is shown on the right. And we looked at this particular mineral in detail when we were considering the geometric characteristics of mineral last time in the last lesson. Okay. So, finally, summarizing what we learnt in this lesson, we discussed the chemical composition of the Earth's crust, we discussed the chemical composition of silicate, carbonate, oxide and sulfide minerals. We considered examples of these minerals, and these minerals compose a very large proportion of the Earth's crust. We looked at a list of special characteristics of classes of minerals that arise because of the chemical composition. For example, we looked at the cleavage angles of a double chain and single chain silicate minerals. Okay. And we end finally this particular lesson with a question set. You try to formulate the answers of these questions. The first question is that what is meant by polymorph. You give an example of a polymorph mineral of pure carbon. Now, second question that I ask is, can you provide a reason for mechanical strength of quartz? You give a qualitative reason why quartz is so strong and inert. How would you distinguish hematite and magnetite mineral is the third question. Fourth question is, how would you distinguish olivine and quartz minerals? And finally, can you provide a reason for acidity of subsurface soils containing sulfide minerals? In fact, the ore bodies that contain sulfide mineral, that is actually a very common source of mineral of different economic minerals. Sulfides are a very common source of several different economic minerals, and these areas are often affected by acidity and consequent loss of fertility of the within the area where the mine waste is dumped. Now, what I ask here is that can you give the reason why subsurface soils containing sulfide minerals would exhibit acidity? Try these questions in your spare time, and I will also give you my versions of the answers when we meet next time for the next lesson. Thank you very much. Hello everyone, and welcome to a fresh lesson on the engineering geology. Today we are basically going to talk about origin and types of rocks, and also we are going to look at the different types of rocks that are commonly available, normally found across the country of India. But before we actually proceed with the subject matter of today's lesson, we are going to consider the questions that were asked the last time when we met, and this is the question set that you already have. The first question was, what is meant by polymorph, and I also asked you to give an example of a pair of polymorph of pure carbon mineral. Now, polymorph is actually are a bunch of minerals which have the same kind of chemical composition or chemical formula, but they have got different crystallographic geometry or different structure really. Now, two polymorphs of pure carbon mineral are graphite, which is essentially a sheet which has got a sheet structure like what we had for sheet silicates, and then you have got diamond, which is basically which has got a pair of tetrahedra, and essentially conglomerate, essentially volcanic rocks and metamorphic rocks that generate out of volcanic rocks. So that in a nutshell gives you the inventory of different types of rocks found across our country. Is still used in getting insight about the rock forming processes. What Bowen proposed was the fact that minerals actually change their characters as the temperature comes down, and there are two classes of minerals, one along the discontinuous series shown on the left here. These are the ones. This is the class of minerals on the discontinuous series, and then you have got another class of mineral that form a continuous series as schist and essentially conglomerate, essentially volcanic rocks and metamorphic rocks that generate out of volcanic rocks. So that in a nutshell gives you the inventory of different types of rocks found across our country. Okay. To summarize the lesson then, what we learnt in this lesson include the definitions of general terms like rock and soil. We had discussions on rock forming processes. We also looked at a list of main rock forming minerals and examined their weathering characteristics or susceptibility to weathering. Then we looked at different types of rocks: volcanic, metamorphic and sedimentary. Looked at rock cycle and looked at rocks that are found in different parts of our country. That brings us to the end of this presentation. So we close with a question set which you should try answering in your spare time. The first question is that how in general would you expect the percentage of oxygen to change in a silicate mineral with weathering? Second question is, which of the two minerals abundant on Earth's crust would be more resistant to weathering, quartz or feldspar? Third question is, what is meant by diagenesis? And fourth one is how magma can remain in a partially molten state. Try answering these questions. I will help you out with the answers when we meet in the next time. So that ends this lesson, and thank you very much for listening to me. So until I meet you the next time around, bye for now.